Chapter 9.3. In this lesson, we're going to identify properties of rational functions, and we're going to learn how to graph rational functions. Okay, so today we're going to learn rational functions and point of discontinuity. So let's talk about what a rational function is. A rational function is nothing more than a function that is just p of x over q of x, where p of x and q of x are polynomial functions, and obviously the q of x cannot equal 0. Graphs of the rational functions are shown below. Alright, so y equals negative 2x over x squared plus 1 gives you kind of a squiggly line. Y equals 1 over x squared minus 2 gives you 3 separate sections. Y equals x plus 2 times x minus 1 all over x plus 1. And he gives you the two graphs like that. In the first rational function, there's no value of x that makes up the denominator, so the graph is continuous. Alright, because it has no jumps, breaks, or holes in it. It can be drawn with a pencil that never leaves the paper. The second rational function, x cannot be 2 or negative 2. Alright. And the third function, x cannot be equal negative 1. The last two graphs are discontinuous. If a is a real number for which the denominator of the rational function is 0, then a is not the denominator of f. The graph of f is not continuous at x equals a, and therefore the function has a point of discontinuity at x equals a. Okay, to find points of discontinuity, all you have to do, and here's the key, find the values of x and make the denominator 0. Alright, so let's find the points of discontinuity. Okay, a. X squared plus 2x plus 1 is the denominator, so let's factor it. X squared plus 2x plus 1. If you need to x factor, you can. Product of 1, sum of 2. So we learn, that's a perfect square trinomial, so it'd be 1 and 1. So it's going to be x plus 1 squared. So to solve that, x cannot equal negative 1. So the point of discontinuity is x equals negative 1. Let's look at the next one. X or y equals negative x plus 1 over x squared plus 1. The function is undefined at values of x where x squared plus 1 equals 0. So x squared plus 1, alright, I'm going to do a little bit different in the book, cannot equal 0. So x squared cannot equal negative 1. Well, x squared can never be a negative number, so there is no point of discontinuity. So let's move on. Alright, 1a. Well, that's a perfect square, so that can be rewritten as x minus 4 times x plus 4. So x cannot equal 4, and x cannot equal negative 4. Remember how we solved that one and that one. So the answer is B. 1b. Alright, any points of discontinuity. The only thing we got to worry about right now is the denominator. So x squared plus 3 cannot equal 0. X squared cannot equal negative 3. Well, that'll never happen, so there's none. Alright, 1c. So I have x squared plus 2x minus 8 cannot equal 0. So let's x factor this thing. My c value is negative, a times c is negative 8. My b value is 2. So two numbers that give me a product of 2 and a product of negative 8 and a sum of positive 2. So 4 and negative 2. So I can rewrite this as x plus 4 times x minus 2 still cannot equal 0. So x cannot equal negative 4 and x cannot equal 2. The answer is D. Okay, you see how we grouped them? Again, that's chapter 2 or 3 stuff, so we shouldn't need to review that. We shouldn't how to factor polynomials. Alright, and then we just found the roots. And then since it cannot be 0, we set it not equal to. Alright, so let's look at this for a second. The graph of y equals x plus 1 over x minus 1 times x plus 2 is shown at the right. The zeros are 1 and negative 2. So what you notice is x can never be 1 or negative 2. So we draw dotted lines, and those become asymptotes, or vertical asymptotes. So whatever the denominator cannot be in some graphs will be the asymptotes, vertical asymptotes. Okay, let's look at the second one. 2 is a 0 for both the numerator and the denominator for the function y equals x minus 2 times x plus 2 all over x minus 2. The graph of this function can be simplified as y equals x plus 1. But it has a hole at 2. There's no vertical asymptote there. It's just a hole. Since you can cancel it out, here's the easy rule. If you can cancel it out, it's a hole. If you cannot cancel it out, it's a vertical asymptote. Now again, all of this applies to the denominator. So let's look at this one. 2 is a 0 of both the numerator and the denominator of the rational function y equals x minus 2 over x minus 2 times x minus 1. The graph of the function, once it's simplified, is nothing more than y equals 1 over x minus 1, except it has a hole at 2. So we knew we had points of discontinuity at x equals 2 and x equals 1. Since we were able to factor out x equals 2, that becomes a hole. Since we weren't able to factor out x equals 1, that is a vertical asymptote. And you can see in the diagram, there's the hole, and there's the vertical asymptote. All right, last example. 2 is a 0 of both the numerator and denominator of the rational function x minus 2 over x minus 2 squared. The graph of this function is the exact same graph as y equals 1 over x minus 2. So their vertical asymptote is x equals 2, so you notice there is no hole. Okay, moving on. So vertical asymptotes. A rational function, p of x over q of x, has points of discontinuity for each real 0 of q of x. If p of x and q of x have no common real zeros, then the graph has vertical asymptotes at all the real zeros of q. Basically saying, if you can't factor them out, they're a vertical asymptote. P of x and q of x have common real zeros, a, then there's a hole in the graph. And what we're saying here is if you can factor out the denominator, that becomes a hole. That zero value becomes a hole. So finding vertical asymptotes. Okay, describe the vertical asymptotes in the holes. Well, I can't factor anything out in the first one, so 2 and 3 are vertical asymptotes. Next one. 2 is a point of discontinuity. I can cancel it out, so it's a hole. All right. I've got points of discontinuity at x equals 3 and x equals negative 4. I can cancel out the negative 4's, so that's a hole. I cannot factor out all the 3's, so it is the vertical asymptote. Hopefully that makes sense. All right, describe the vertical asymptotes and holes of each one of these. All right, so I have points of discontinuity at x equals 1, just making that 0, and x equals negative 3. Can I factor either of them out? No, so they're both vertical asymptotes. All right, I have points of discontinuity at x equals 2 and x equals negative 3. I can cancel out x equals 2, so that's a hole. And I cannot factor out x equals negative 3, so that's a vertical asymptote. So I have a hole at 2 and a vertical asymptote at x equals negative 3. All right, x squared minus 1 over x plus 1. Well, that factors to x plus 1 and x minus 1. So it's over x plus 1. So I have a point of discontinuity at x equals negative 1. I can cancel that grouping out, so that becomes a hole. So I have a hole at x equals negative 1. Okay. So for the graph of rational functions such as y equals 1 over x and y equals 1 over x squared, the horizontal asymptote is y. As shown to the left, when the absolute value of x is large, the graph is very close to the graph of y equals 1 over x squared. So y equals 0 is the horizontal asymptote of both graphs. In fact, y equals 0 is the horizontal of asymptotes over a graph of any rational function if the degree of the denominator is greater than the degree of the numerator. If the degree of the numerator equals the degree of the denominator, then a horizontal asymptote can be found as shown below. So let's zoom in and let's check it out. Find the horizontal asymptote, remember horizontal is going this way, of y equals 3x plus 5 over x minus 2. Well, we're going to have to do a little bit of math. We're going to have to divide. So let's check out what they did. So we're going to divide the denominator into the numerator. Remember how we did this. X minus 2 goes into 3x plus 5. You're going to multiply it by 3. So I get 3x minus 6. Again, I took 3 times x, 3x, put it right below. 3 times negative 2 made it negative 6, put it right below. Now change the signs and subtract, and I got 11. Okay, so I have a remainder of 11. It went in 3 times. So I can rewrite my graph now, or my function, which was y equals 3x plus 5 over x minus 2. Now I can rewrite it as, what's my remainder? That goes on top, so it becomes 11 over x minus 2 plus whatever my divisor was, 3. So that's my new equation. So it tells me my horizontal asymptote is 3. Because if you remember this, y equals a over x minus h plus k. K is my vertical translation, and h is my horizontal translation. So I have a horizontal asymptote at 3, and I have a vertical asymptote at 2. All right, find the horizontal asymptote of the graph. All right, so x minus 1 goes into negative 2x plus 2. Goes in negative 2 times, so it becomes negative 2x plus 2. Change the signs. We have 4. It doesn't say solve for the equation. It says find the horizontal asymptote. So that'll always be the horizontal asymptote. So y equals negative 2. All right, 3b. Find the horizontal asymptote. So x squared plus 1 goes into 2x squared plus 5. That'd be 2. So that'd be 2x squared plus 2. Change signs. So I got 3. So y equals 2. Okay. So here's something I could have showed you before and saved you a little bit of time. The graph of a rational function has at most, if it has any, a 1 horizontal asymptote. If the graph of a rational function has a horizontal asymptote of y equals 0, if the degree of the denominator is greater than the degree of the numerator, that means if I have an x squared on bottom and anything less than that up top, the horizontal asymptote, if it exists, is y equals 0. If the degree of the numerator and the denominator are equal, the graph has a horizontal asymptote of y equals a over b, where a is the coefficient of terms of highest degree of the numerator and b is the coefficient of highest degree terms of the denominator. If the degree of the numerator is greater than the degree of the denominator, then it has no horizontal asymptotes. All right, sketching the graphs. Okay, once you identify the vertical asymptotes in the holes, you can go ahead and plot those, and then the easiest way to do it is just find values for y or x near the asymptotes, and then just plot, plug and chug, and then plot and sketch. So again, calculate the values of y for the values of x near the asymptotes. So again, plot the asymptotes first, and then just pick points near. All right, sketch the graph of y equals x plus 3 over x minus 1, x minus 5. So let's look. We know we're going to have vertical asymptotes at x equals 1 and x equals 5. So A is still a possibility, C's out, B is still a possibility, D is a possibility, but we know it's going to continue on to the right, so we can rule out D, we can rule out C. Now let's just pick a number and plot points. So when x equals 3, let's plug points in. So that would be 6 over 2 times negative 2. So I know that's going to be a negative number. That's going to be negative 6 over 4